Properties of inverse functions. So in a previous video, we talked about what inverse functions are, and let's talk about why they're useful. What can they do? What is their deal? So big one is that when you compose a function with its inverse, the result will always be x. So f inverse composed with f is equal to x, and f composed with f inverse is equal to x. And that's really cool because if you think about what's happening here, it's like they're canceling each other out. We don't we don't need to necessarily just have an x in here, right? It could be anything in here. It's saying that whatever, if you take f inverse of f of whatever, those things cancel and you're just left with what's inside. So f and f inverse cancel each other out. So if I have f inverse of f of 5, this is just 5. They canceled each other out. And this would work additionally if we had f of f inverse of, it could be other stuff in here. It could be 2x squared plus 7, and they cancel each other out. You're left with 2x squared plus 7. Another fun fact about inverse functions, if you have the point a comma b on the graph of f, then b comma a is on the graph of f inverse. We talked about that, right? That's how we defined what an inverse was. We said it inverts the x and y coordinates. But if we take this back to what our function notation tells us, if a comma b is on the graph of f, that means that f of a is equal to b. And if b comma a is on the graph of f inverse, that means that f inverse of b is equal to a. So these two relationships always exist at the same time. If f of a is equal to b and f inverse exists, then f inverse of b is equal to a. And that's what I have written down right down here. And I wanted to make a quick note on this. If you have f of 8 equals -4, this rule right here tells you if f of 8 is equal to -4, you can say that f inverse of -4 is equal to 8. Another fun thing about inverse functions is that the domain and range of a function flip-flop and become the range and domain of the inverse. So if you have a function f and he has a certain domain, then f inverse has that domain as its range. And the range of f becomes the domain of its inverse. Now, this makes sense when you logically think about what an inverse does. It makes sense that the set of x values, which is what a domain is, of a function becomes the set of y values, the range of its inverse, right? That's literally what we said would happen. We said the x and the y will flip-flop, so it would make sense that the set of x values become the set of y values for the inverse, and the set of y values for the original become the set of x values for the inverse. This is actually a really useful thing though, because sometimes finding things like range can be really difficult. And oftentimes finding domain is a much easier thing to do. So sometimes when we want to find the range of a function, it's actually easier for us to find the domain of its inverse, to find an inverse and then find that inverse's domain. Now, how do we find an inverse? Well, you'll have to find out in another video. That'll be the next video. Um, but in this video, we're going to we're going to figure out how to tell if two functions are inverses of one another. But this fact right here is really, really useful when it comes to finding ranges for functions that it's hard to find ranges for. You just find the inverse function and find its domain. All right, let's do some examples of are the following functions inverses of one another? Again, the big idea is that in either way, in either composition direction, if you compose them together, you get x. And you do have to check both directions, both f inverse of f of x, if that is x, and is f of f inverse of x, x. So you have to check both directions, make sure they both come out to x, and then we can say that they are inverses of one another. So I'll make a note right here. So we need f of f inverse of x to be x, and we need f inverse of f of x to be x. I'm going to start with doing, oh, and because we don't have f inverse, this is actually g. So we need f of g of x to be x. We need g of f of x to be x. We don't know that these guys are inverses of one another yet, so there's nobody labeled f inverse. We're just wondering if we compose them in both directions, do we get x? So let's start with f composed with g of x. So we have f composed with g of x So I'm plugging g of x into f. So f of 2x minus 1. Now, f is this function here. So what I'm doing is I'm plugging 2x minus 1 in for x in this function. So the function f of x would have been 1/2 x plus 1/2, but it is no longer an x in here. It's a 2x minus 1. If I distribute this 1/2, 1/2 times 2x is just x. 1/2 times 1 is minus 1/2. And then we have that plus 1/2 at the end. All right, we get x. That's good. It's a good start. Let's check the other composition direction. So g of f of x. So we're doing g of f of x. Plugging f of x in, we get g of 1/2 x plus 1/2. So g is the function 2x minus 1. But instead of x, we're putting in this guy here, right? So instead of x, just a little bit of review on composition of functions. We're putting in 1/2 x plus 1/2. I'm going to distribute the 2. 2 times 1/2 is 1, so we have x plus 1 minus 1, we get x. So in both directions, when I do the composition, I get x. So f and g are inverses of one another. So what does that mean? Well, it means that f inverse of x is 2x minus 1, right? That's what g is. So f inverse is 2x minus 1, and it means that g inverse of x is 1/2 x plus 1/2. So this inverse relation is a relationship that they share with one another. Let's go ahead and try one more problem like this. So we'll do f composed with g of x, and we'll see if we get x out, and then we'll do g composed with f of x. So we have f of g of x is 3x plus 1. So I'm plugging 3x plus 1 in for x in here. And I know this gets a little confusing. So here's this 3. Okay, this 3 right here is this 3 right here. Instead of this x, I'm putting in 3x plus 1. 3x plus 1. So this x is a 3x plus 1, and then I have this minus 1 at the end. Distributing, I'm going to get 9x plus 3 minus 1. I get 9x plus 2. That's not good. So if we do this composition and we don't get x for the first direction, you're done. You don't have to do anything else. If one direction doesn't work, that's it. That's it. Um, they're not inverses of one another. F and G are not inverses of one another. It's also not enough for one direction to be correct. So I can't stop after just doing one direction, nor do I need to continue doing this problem if I do one direction and it doesn't end up being x. If I do a direction, it doesn't end up being x, then I'm done. You don't have to go any further. Anyway, so that's how we determine whether or not functions are inverses of one another. We just compose them with one another and make sure that they quote unquote cancel each other out. So in our next video, which will be our last video of this section, we're going to talk about how to find inverses of functions. Not just are they inverses, but how do we find them? So I'll see you in the next video for that.